Good morning. All right, I'm going to start off with a bit of a pass around, so I hope you guys can catch. Because I just distributed something that you'll see later on in the presentation, and I just did a little bit of an Oprah. So my name is Anne, and I deal with origami, and I want to show how in geotechnical engineering this can actually be applicable too. I'm at the University of Illinois, and I come to you as a structural engineer. I know, I've gotten mixed reactions of, oh wow, okay, and well, this meme, spoke to me. We've heard a lot about adaptive sustainable design today and yesterday, and I come to you as a structural engineer, almost a mechanical engineer working in deployable structures. So we are one and the same. The idea of an adaptive structure, you can think of, NASA's been doing it for such a long time. You can think of a space telescopes, but how do we translate that to on-world applications, something we can see day to day? So there's a few examples you have here. You have on the left-hand side a 10-story tall demonstrator tower at the University of Stuttgart that has actuators in the diagonals that can change the deflection of that whole structure to address wind loads. Pretty wild. It's basically a tall building robot. You have a bridge that is a very slim section, can adapt to people walking on it in real time to negate deflection. You have adaptive facades. You may have seen this more likely in popular media that can address solar and thermal needs of a building. So you're thinking about architectural needs within a building. You can have a very thin wood structure that can change its shape to address the load with such a small cross-section in comparison to traditional methods. And you can also look at what looks like a real space structure called a tensegrity structure that can change its slope by using, again, actuators, a bit of robotics, but at a very large scale. So I'm a structural engineer, but I got into robotics, and this is something that you can deploy. You can do large shape changes and addressing needs such as installing a structure like this in a hard-to-reach area, a remote region. Things that can also help with this is having sensors, being able to learn about the structure. If something is damaged, where is it damaged? How do we fix it? And can we actually get the structure to heal so we can still have it in use throughout its lifetime rather than having to put the caution tape across it and hope that people are not using it? So that's where I came from. When we're thinking about flat pack, something transporting to site. Now, this concept will come to geotech momentarily, I reassure you. But you think about origami, this idea of this is a pill bug inspired origami, something that's nice and flat, because I was in my garden. You poke a little pill bug and it rolls into a ball. It depends on where you are within the United States or in Canada. That could be a roly-poly or an armadillo. They all kind of do the same thing. I know, I go across different places and I have to have a different analogy. But this idea of flat pack, I was thinking, okay, if we can transport it with less space, but then we can roll it onto site, this is really opening up a lot of opportunities. So here you have about a meter scale structure we have in a lab made out of wood. And the idea is that it can roll. We can roll it into a structure. We can have a temporary structure put onto a construction site, thinking emergency help after a natural disaster. So this is something that we're really excited about. And how can we get structural engineering and geotechnical engineering to merge together, to work together on this concept? And so here I have also another piece of origami. I came with models today. I wasn't in class, but I still had to do my demonstrations. So you have a piece of origami. You can have your flat foldable with hinges. It can transform into a much more compact section. So we can prototype these things. We can do it at a smaller scale and building them up. And this is going to build into what we're going to do next, talking about geotechnical engineering. I'm going to warn you, there's math on the next slide. I know, it's a little early for math. But it's pictures, yay! So we first start off with the concept of origami. And then we look at piles. We look at anchors, origami, and piles. Coming up with this concept that if you're kind of tinkering around with the little thing that's coming around playing around with it, this idea of a compliant hinge, something that folds out, a fin on the outside of a pile that we can engage more of the soil, especially for tension capacity of a pile. We can then utilize less material. These things can compact to a much smaller state, transform to site, thinking further distances. We can save on fuel, we can save on the material, be more efficient in thinking about how we use this material. So this is what we've been working on, the idea of origami, but in a geotechnical application. Now, first started off with this idea, going hiking, you have these cheatgrass seeds that get stuck in your sock and they keep burrowing and burrowing. Annoying while you're hiking. This concept would be really interesting. That was our first trial. What about if we can get an anchor that burrows in, just like an anchor you would find at Home Depot, but at a larger scale? So this is what we tried. This was kind of middle of the pandemic. There was a fish tank full of sand, so that was at least where we started. Even better yet, we have that vertically driven pile, but we have vibration. We have, if it's a marine environment, we don't want to impact the soils around it. Can we have that torque driven along with that vertically driven pile behavior? Now, if we start looking at biology again, kind of a theme, we can actually program in different stiffnesses into that material to make those fins, when they fan out, to also become scoops. Now it's going to be much more challenging in a tension-loaded pile to take them out. We're having a lot more effective use of material with just those little fins. Here I wanted to spend some time talking about the challenges, and this is great having it after our panel. We have two main challenges. We have the climate change challenge and we have the science challenge. And this is where structural engineers, mechanical engineers, and architects have now been able to work with this idea within a geotechnical context. The call to action is having all those disciplines work together for such a less typical design. The first thing is that climate change challenge. It's not only to design for new infrastructure. We're not just creating new structures, which the pile is part of a structure. So that deployable on, that fin that comes out, that is an add-on to a concept that's already been done. But we want to complement the existing infrastructure. We don't want to, replace this entire building with an adaptive structure. That doesn't make sense. But adaptive components will definitely enhance and protect our existing assets, as we were just talking about previously. And so this is the best complement of new science, but also to protect what we already have. And that science challenge is looking at adaptive structures. Will provide those opportunities for modeling and testing, but at those intersections between structural engineering and geotechnical. I come to use kind of like an adopted into the geotechnical community, but it's really that cross-section of the two that have made this work really interesting. The actual capabilities of this work is just, there are a lot of possibilities in terms of coastal resilience, in terms of offshore, long distances, anything that we have to transport to site is where it's critical. So I leave you with this one image here, and this is a comparison of when we have a pile with these deployable fins on them, 1, 2, or 3. We're looking at surface area, because obviously for tension piles, this is something that's critical. And we can see the volume of material for the equivalent for 3 fins is so much larger. So if we're looking at tension as a critical, you're using all that material in the center of the pile, and that's not serving that particular use. Obviously, there's other uses. You guys know those very full well. But trying to be effective in our use of material, so talking with our steel industries, concrete industries, to make better use of it, not just trying to sell more of that material. So that is my call to action, is to use materials more effectively with novel concepts like deployability, like adaptive structures, and to incorporate those when they make sense, remote regions, for example. So that's it from me as your friendly neighborhood structural engineer. Thank you very much.